Welcome to G Fun Facts Online, where we dive deep into the hidden mechanisms of our world. Today we are stepping into the cathedral of modern computing to examine a quiet crisis that is defining the future of artificial intelligence. For decades, the tech industry worshipped at the altar of Moore's law. We relentlessly doubled transistor counts and clock speeds, assuming that if we could just think faster, we could solve the world's problems. We built processors capable of executing trillions of operations per second and designed neural networks with hundreds of billions of parameters. We constructed supercomputers that consume the power of small cities, but in our quest for raw processing speed, we forgot one fundamental truth. A brain is useless if it cannot remember. As we stand here in 2026, the artificial intelligence revolution, the defining technological shift of our century, is not being throttled by a lack of computational power. It is being throttled by a lack of memory bandwidth. The GPU, once the undisputed king of the hill, now often sits idle for microseconds at a time, starving for data that cannot be fed to it fast enough. The culprit and the savior is a technology known as high bandwidth memory, or HBM. This is the story of HBM, the most complex, expensive, and critical component in the modern computing stack. It is a story of physics, where engineers fight against heat and resistance at the atomic scale. It is a story of geopolitics, where nations vie for control over the supply chain of what is now called AI gold. And it is the story of the memory wall, the single greatest barrier standing between us and the next leap in artificial intelligence. To understand why HBM is so revolutionary, we must first understand the tyranny of the von Neumann bottleneck. Since the dawn of the digital age, computers have been architected with a separation between the processing unit and the memory unit. Data must travel back and forth between these two components through a bus, which is essentially a digital highway. For 40 years, we relied on GDDR, or Graphics Double Data Rate Memory. GDDR is planar. It sits on the motherboard next to the processor, connected by copper traces printed on the circuit board. It is reliable, cheap, and fast enough for video games. But as AI models grew from mere gigabytes to terabytes in size, GDDR hit a physical limit. To get more bandwidth, you needed wider buses, which means more wires. But you can only fit so many wires on a 2D motherboard before signal interference and power consumption become unmanageable. This is where high bandwidth memory enters the picture. HBM is not just a better memory chip, it is a paradigm shift in 3D packaging. Instead of placing memory chips side by side on a motherboard, HBM stacks them vertically, like floors in a skyscraper. The real magic of HBM lies in a technology called the through-silicon via, or TSV. In a standard memory chip, data travels to the edge of the silicon die to exit through pins. In HBM, engineers drill thousands of microscopic holes through the silicon die itself. These holes are filled with conductive metal, usually copper, creating vertical elevators that allow data to shoot straight up and down the stack. A single HBM stack can have thousands of these TSVs. This allows for an interface width that is orders of magnitude wider than traditional memory. While a standard GDDR6 chip might have a 32-bit wide interface, a single HBM stack operates on a 1024-bit wide interface. With HBM4, this doubles to a staggering 2048-bit interface. It is the difference between a Ferrari on a 2-lane road and a freight train on a 1,000-lane highway. The Ferrari is faster in terms of clock speed, but the freight train moves significantly more cargo, providing higher bandwidth. However, you cannot simply solder an HBM stack onto a standard plastic motherboard. The connections are too dense, numbering in the thousands within a few millimeters. To solve this, the industry invented the silicon interposer. The interposer is a passive slice of silicon that sits between the GPU and the HBM stacks. It acts as an ultra-high-density bridge. Because it is made of silicon rather than fiberglass, it can support wires that are nanometers thin. This 2.5D packaging allows the HBM to sit millimeters away from the GPU, reducing the distance data must travel, thereby slashing power consumption and latency. Let's look at the evolution of this technology from 2013 to where we are now in 2026. The history of HBM is a relentless march toward density and speed. The first generation, HBM1, arrived in 2013. Championed by AMD and SK Hynix, it was a technological marvel, but a commercial niche. It offered 128 gigabytes per second of bandwidth per stack, which was impressive for the time, but it was limited to 4 gigabytes of capacity. It proved the 3D stacking concept worked, but the manufacturing yield was low, and the cost was astronomical. Then came HBM2 and HBM2E between 2016 and 2020. This era brought the technology to maturity. Bandwidth doubled to 256 gigabytes per second per stack, and capacities grew to 8 gigabytes. This was the era where NVIDIA's Tesla data center cards began to pull away from the competition. HBM2E later pushed speeds to 460 gigabytes per second, becoming the standard for the early AI boom, effectively the GPT-2 era. The turning point was HBM3 in 2022. With bandwidths hitting 819 gigabytes per second per stack, it enabled the NVIDIA H100 Hopper GPU to train massive large language models like GPT-4. HBM3 allowed for 12 high stacks, meaning 12 dies stacked on top of each other, pushing capacity to 24 gigabytes per chip. A single H100 with 6 HBM3 stacks offered 80 gigabytes of ultra-fast memory. As of late 2025, HBM3E became the dominant force. It is an optimization of HBM3, pushing speeds to 1.2 terabytes per second per stack. SK Hynix and Micron led this charge, utilizing 1B nanometer DRAM nodes. The E stands for extended, but it effectively meant essential for the Blackwell generation of GPUs. HBM3E enabled 12 high and 16 high stacks, delivering up to 48 gigabytes per package. Now, we arrive at HBM4 in 2026. This is the biggest architectural shift since the inception of HBM. The interface width doubles to 2048 bits. To keep power in check, clock speeds are moderated, but the massive lane count ensures bandwidths exceed 2 terabytes per second per stack. Crucially, previous HBM generations used a simple buffer die at the bottom of the stack. HBM4 allows this base die to be a logic process, like 12 nanometers or 5 nanometers FinFET. This means the memory controller can move inside the memory package, or even perform basic computation right at the source of the data, a concept known as processing in memory. Furthermore, the vertical height constraints are so severe that traditional microbumps, the solder balls between layers, are becoming a liability. HBM4 pushes the industry toward hybrid bonding, which involves fusing copper directly to copper without solder. You might be wondering, if this technology is so vital, why is it the bottleneck? Why can't we just make more of it? The answer lies in the extreme difficulty of its manufacturing process. Making HBM is less like manufacturing a car, and more like building a watch while wearing boxing gloves. The first major hurdle is the yield trap. A standard DRAM wafer might yield 90% good chips, but HBM requires stacking 8, 12, or 16 of these chips. If one chip in the stack is defective, the entire stack is trash. Mathematically, the yield loss compounds. If a single die has a 98% yield, a 16-high stack has a yield of roughly 72%. In reality, the mechanical stress of stacking lowers this further. This makes HBM exorbitant to produce. Then there is the thermal battle. The two Korean giants, SK Hynix and Samsung, took different paths to solve the heat and stability problem. Samsung and Micron traditionally used TCNCF, or thermal compression with non-conductive film. They place a non-conductive film between layers and use heat and pressure to melt the solder bumps. It is robust, but can be slow and prone to bending or warpage as the stack gets higher. SK Hynix, on the other hand, bet on Mr. MUF, or mass reflow with molded underfill. They attach the chips and then flood the gaps with a liquid epoxy molding compound. This liquid fills the voids and cures into a hard, heat-dissipating stone. Mr. MUF proved superior for heat dissipation and production throughput in the HBM3 era, giving SK Hynix a massive lead in yields and market share, reaching over 60% in 2025. However, as we move to 16 high stacks in HBM4, the gaps between chips are becoming so small that even liquid epoxy struggles to flow. This is forcing a convergence toward hybrid bonding, where there are no bumps at all, just perfectly polished copper surfaces held together by atomic forces. The market landscape in 2026 reflects these technical battles. It is an oligopoly defined by technical capability. SK Hynix is the king of the hill. They bet the farm on HBM when others hesitated, and it paid off. By perfecting Mr. MUF, they became the primary supplier for NVIDIA. In 2026, they still command over 55% of the market. Their HBM3E is the gold standard, and their HBM4 yields are reportedly the highest in the industry. Samsung Electronics, the sleeping giant, has woken up. Samsung was famously late to the HBM3 party, suffering from yield issues with their TCNCF process. However, 2026 is their comeback year. By adopting a hybrid approach and leveraging their turnkey service, offering memory, foundry, and packaging all in-house, they are clawing back market share, aiming for 30%. Their Shinebolt HBM3E and subsequent HBM4 designs are now qualified in major hyperscaler chips. Then there is Micron Technology, the American contender. Micron holds about 20% of the market. They skipped HBM3 to jump straight to HBM3E, a risky move that succeeded. Their 1-beta manufacturing node is highly efficient, and their HBM3E consumes roughly 30% less power than competitors, making them a favorite for power-constrained data centers. But let's clarify what we mean by bottleneck. In this context, it is literal. First, there's the capacity versus compute ratio. AI models are growing faster than memory density. A single GPU cluster might have petaflops of compute, but only terabytes of memory. The GPUs spend vast amounts of energy simply waiting for data to be fetched. Second, there is the supply chain choke. There is a limited global supply of the specialized equipment needed to make HBM. The thermocompression bonders and TSV etchers are backordered for 18 months. You cannot simply spin up an HBM line. It takes 2 years to build and qualify a facility. And finally, the thermal wall. HBM stacks run hot. They are placed millimeters from a GPU that runs at 80 degrees Celsius. Memory cells leak data when they get hot. If they get too hot, above 95 degrees, they lose data entirely. To prevent this, the refresh rate of the memory must be increased, which consumes more power and generates more heat. It is a vicious thermal cycle. The industry is currently designing liquid cooling that touches the silicon directly to solve this. Looking ahead to the latter half of 2026 and into 2027, the roadmap is clear but treacherous. We are seeing the rise of custom HBM. With HBM4 allowing a logic-based die, customers like NVIDIA and Google are asking to design that base die themselves. They want to put their own proprietary logic into the memory stack. This changes the business model of memory from selling commodities to foundry services. HBM is essentially becoming a custom ASIC. Beyond that, we are looking at optical interconnects. Eventually, copper wires will fail us. The resistance is too high at HBM speeds. The holy grail is to replace the electrical traces on the interposer with light. Companies are experimenting with co-packaged optics, where the HBM communicates with the GPU via photons, virtually eliminating heat and latency over distance. Is there an HBM5? Yes, but it may look very different. We are approaching the height limit of physical stacking before the stack becomes mechanically unstable. Future memory might move to 3.5D structures or utilize capacitorless DRAM to increase density without height. In conclusion, high bandwidth memory is the unsung hero of the AI age. It is the most sophisticated component in your AI accelerator, a marvel of vertical integration and atomic precision. It is also the most fragile link in the chain. The shortage of HBM is the primary reason why AI accelerators cost as much as a luxury car. As we navigate 2026, the resolution of the HBM bottleneck will determine the pace of AI progress. If the engineers at SK Hynix, Samsung, and Micron succeed in yielding HBM4 at scale, we will unlock the next generation of intelligence. If they fail, the AI revolution will face a long, hot, and expensive summer. In the end, the bottleneck is not just silicon. It is the fundamental physics of moving information through space. And in this battle against physics, HBM is our sharpest weapon. Thanks for tuning in to G Fun Facts Online.